4.4. Fitting a Poisson distribution. A. From the frequency distribution, find the mean x bar. B. Use the mean x bar as a parameter of Poisson distribution. Generate the Poisson distribution for x follows a Poisson lambda as x bar. C. To find the theoretical expected frequencies, multiply each probability found by total frequency of the given distribution. Let us look at example 19. The number of phone calls received over a period of 150 days was recorded as shown. A. Find the average number of calls per day, and B. Calculate the frequencies of the comparable Poisson distribution. For A, we will work out what is x bar. So x bar will be equals to the number of days times the number of calls, which is 0 times 51 plus 1 times 54 plus 2 times 36 plus 3 times 6 plus 4 times 3 divided by total number will be 150, and that will give you 1.04. B. Let us define the random variable. Let x be the random variable, the number of phone calls received per day. So from part 1, we know that part A, so x follows a Poisson distribution with lambda as 1.04. Multiplying the probabilities by 150 and rounding off to the nearest integer gives the theoretical Poisson distribution frequencies. This can be done by keying in y1 is equals to Poisson PDF with lambda as 1.04 and x as an unknown, and y2 is equals to 150 times y1, and with y1 we are going to call out this table of values, which is as shown on the right, and y2 will give the corresponding values, which is shown in the table. The distribution of two or more independent Poisson variables. If x and y are two independent Poisson random variables with parameters mu and lambda respectively, that is, x follows a Poisson mu and y follows a Poisson lambda, then we can say the sum, which is x plus y, will also follows a Poisson distribution with a new mean as mu plus lambda. The above result can be extended to three or more independent Poisson random variables. If x1, x2 to xn are n independent observations of Poisson random variable x with parameters lambda, then we can say that x1 plus x2 plus until xn will follows a Poisson distribution n times of lambda. Example 20. During a certain morning, the number of people entering a certain LRT station per minute has a Poisson distribution with mean 3, and the number of people leaving the station per minute has an independent Poisson distribution with mean 2. A. Find to three significant figures the probability that during a particular minute in the morning, 1. Not more than one person will enter the station, 2. No one will enter or leave the station, and 3. Exactly one will enter the station given that the number of people entering and leaving the station during the particular minute is exactly 4. B. Determine the least number n such that the probability of not more than n people leaving the station in the 30-second interval is greater than 0.95. A. Let us define the random variable, the number of people entering a certain LRT station per minute, and y be the random variable, the number of people leaving a certain LRT station per minute. Since x and y are independent, therefore x follows a Poisson distribution with 3 and y follows a Poisson distribution 2. A. Part 1. To find the probability where it is not more than 1 will enter the station means it's the probability of x less than equals to 1. And using a GC, you end up with 0.199. Part 2. The probability that no one will enter or leave the station means probability of x equals to 0 where no one enters, probability of y equals to 0 where no one leaves. And using a GC as well, you get the value as 0.00674. Part 3. To find the probability exactly 1 will enter the station given the number of people entering and leaving the station is equals to 4. Take note that in part 3, this is a conditional probability. And we need to know what is the new random variable, which is the sum x plus y will follows a Poisson distribution 5. The required probability will be probability of x equals to y given that x plus y is equals to 4. This is a conditional probability. And if you recall conditional probability, probability of x given y is equals to probability of x intersect y over probability of y, which gives rise to probability of x equals to 1 intersect x plus y equals to 4 divided by probability of x plus y equals to 4. Take note that at the numerator we have probability of x equals to 1 already, and since x plus y must be equals to 4, therefore probability of y must be 3 divided by probability of x plus y equals to 4, and using a GC you'll be able to get 0.154. Part B. Let W be the random variable, the number of people leaving the station in a 30-second interval. Take note that the time frame has changed, so we need to define W as a new random variable which follows a Poisson distribution 1. And it is required for you to come up with this important inequality, which is from the statement. The statement says that the least number n such that the probability of not more than n people leaving the station in a 30-second interval is greater than 0.95, which means probability of W less than equals to n more than 0.95. And using a GC, by keying in y1 as Poisson CDF and lambda as 1 with x unknown, and calling out the table of values as seen in the screenshot, you need to look out for values of x or the probabilities which is more than 0.95, and this corresponds to 3, where it is 0.98101. Therefore, using a GC and from the table, the least value of n is 3.